Good morning children, stay safely at home. Now today I am starting the next chapter, that is rotational motion of a rigid body or the moment of inertia. Alright, now you know that only force can produce, when a force acts on a body then it can produce translational motion, alright, and torque can produce rotational motion, alright. And already in the previous chapter we studied that torque or moment of a force is given by this relation, that moment of a force or torque is given by this relation R cross F. Alright, all of you know this, that torque is given by this relation. Okay, I forgot to give that. Now this is the cross product of, in vector chapter also we have studied, it is R cross F. So if I want to explain it through this diagram, let us consider a body is at the point P, a particle is at the point P, and a force F applied on the body, and then this is the position vector R. Alright, so you see torque will be R cross F. Torque is given by R cross F. R is the position vector of the particle and F is the force acting on the particle. Alright, so you see you can write what is the magnitude of the torque. Magnitude of the torque will be R F sin theta, where theta is the angle between R and F. So you see which angle is theta. If I extend this one R vector, then this angle is theta. Alright. Now you see you can break F into two components. You can break F into two components. One is Fr, means the component of the force along the position vector R is known as the radial component of the force. What is the name? It is known as radial component of force, and we denote it by Fr. And if you take the perpendicular component of it, means if you take a component perpendicular to the position vector R, then that is known as tangential component of force. Alright, now tangential component of force we denote it by F theta. Why it is termed as tangential? Because we know at one point radius and tangent, they are perpendicular to each other. Alright, and look at the diagram. This is Fr and this is F theta. So, and this angle is theta. So you can say that if this component is termed as the radial component, then one can term this one as the tangential component. Sometimes we use the term transverse component also. Alright, the component which is perpendicular to the position vector is known as the transverse component or tangential component of force. So just look at the diagram. As this angle is theta, so one can write Fr is F cos theta and F theta, that is the transverse or tangential component, is F sin theta. Alright. So you see, if I apply here that F sin theta is Fr, then you see torque is given by R into F theta. Very important concept in physics. Alright. That means when a force is acting on a body and producing rotational motion, in that case remember that radial component has no role to play for the rotational motion. Only the tangential component is responsible for the rotational motion. Alright. So here you see these are the two formula you must learn and remember. Okay. Torque is given by, torque is equal to R cross F, cross product of position vector and force applied. So one can write torque is equal to R F sin theta, where theta is the angle between R and F. And then the third one is the most important concept, that torque is given by R F theta. F theta is what? The transverse or tangential component of the force. So remember that radial component does not have any role in rotational motion. The rotational motion is created due to the transverse or tangential component of force. Now again, you see, as we know that torque is cross product of R and F. Now R, if you break it into component, you can write it as Xi, Yj and Zk. Like that, force you can break into component along XYZ axis. You can write it as Fxi. Fx is the x component of the force, and you can write it as Fyj plus Fzk. So you see, you can write torque then like this. Already you have done in the, it will be x, y, z. In the vector chapter you have learnt it. So you just form the determinant like this, and then if you break the determinant, I am not explaining once again because I means it will be y into fz minus z into fy plus j means j is z into fx minus x into fz plus k x fy minus y fx. You can write it by breaking the determinant into different parts. So you see, if you consider that tau is equal to tau x means x component of torque, then y component of torque and z component of torque like this, then you see by comparing these two steps, here it is, by comparing these two steps, what you are getting, tau x is equal to y fz minus z fy, tau y equal to z fx minus x fz, and tau z equal to x fy minus y fx. Alright, so these are the x component, y component and z component of the torque. And you see, it is very easy to do. Again, I am just showing you. Suppose you write x, y, z. Then when you are taking x, then it will be y, z first. So you see y, f, z. Alright. Because we are not considering another position vector. We are considering the component of force. So you see, if you get the first term y, f, z, what will be the second term? Z, f, y. Isn't it? Then you see, when you are taking y, then z, x. So it will be z, fx. And then what will be the next term? X, fz. When you are considering z, then it is x, y. So x, fy. Alright. So this is the way you can just write down all the components without this one also. So these are the different components of the torque in terms of the component of the position vector as well as component of force. Now angular momentum of a particle. Alright, you know about the linear momentum. You know that linear momentum is given by product of mass and velocity of the particle. Alright, that linear momentum is given by. Now angular momentum is given by the cross product of position vector and linear momentum. Okay, J is the angular momentum. So how we define angular momentum? Angular momentum is cross product of the position vector of the particle and the linear momentum. So J is equal to R cross P. So you see, just like here you must remember this one, all the concept you have got for torque I am writing, because for torque and angular momentum they are exactly same. You just see, in place of torque, if you write an angular momentum, then F will be substituted by the linear momentum P. So as we have got tau is equal to RF sine theta, exactly like that, J you can write it as RP sine theta. Is that clear? Again, you know here, if this angle is theta, then PR, the radial component, it will be P cos theta, and the transverse component or the tangential component of the linear momentum is P sine theta. So you see, J you can write it as RP sine theta, or you can write it as RP theta. Alright, theta is the subscript, remember, it is not multiplied by. So it is the transverse or tangential component of this one. Another way to write, J is equal to R sine theta into P you can write. So R sine theta is nothing but D, and we write it as P. Our D is the you can say perpendicular component of r, and it is given by r sin theta. Okay, so r sin theta, if you just denote it by d, then you can write j is equal to d into p, or sometimes we write it as r perpendicular into p. So these are the different way we write down the angular momentum. So look at the why I am writing this, because as I said that if one replace tau by j, then f should be replaced by p. Then all the other relations will be same as that of the torque. That's why I am writing it there. Now if you break r into its component xi, yj, zk, and p into its component pxi, pyj, pzk, then you see you can write down the angular momentum this way, just by taking the cross product, finding the cross product. So you just form the determinant py, pz, and then you break it. So what you will get, I is ypz minus zpy plus j is zpx minus xpz plus k into, it will be xpy minus ypx. So you see, if you consider, this is the x component and this is the y component and this is the z component of the angular momentum, then what are you getting? That x component is given by ypx minus xpy, then y component is given by zpx minus xpz, and z component is given by xpy minus ypx. So once again I am saying exactly similar relations you are getting for torque. Only in case of torque it will be xyz and fx, fy, fz, and in case of angular momentum j, it will be px, py, and pz. You will get the relations in terms of px, py, and pz. So these are the relations you have to learn and remember, and already I have given you the tricks that how, instead of mugging up, how one can write down the relation just by forming the circle xyz. Now we have to consider the rotation of a rigid body. So far we considered the rotation of a particle. Alright. Now we are not considering a particle, we are considering a rigid body. So what is the difference? Rigid body consists of several particles, and you can apply the same concept for each of the particle present inside the rigid body. Alright. So let us consider this is the rigid body, and we have taken a particle P with, and the rigid body is rotating about this, rotating in this angle theta. So we have considered a particle P on the rigid body, and let us consider the body is rotating over that arc. So this is the length of the arc. Length of the arc is S. Then you know, arc is given by, length of an arc is given by radius of the circular path, radius of the curve into the angle subtended by it. So you see AC is equal to, this is S, this is S. S is equal to R into theta. So if you take the derivative of both sides, so you can write ds dt is R d theta dt. Alright. Now ds dt, what is this? This is the change in displacement divided by change in time taken, change in time. So ds dt represent nothing but the linear velocity, and d theta is the angular displacement. What is d theta represent? Angular displacement, and dt is the time taken. So angular displacement divided by time taken is nothing but the angular velocity. So you can write v is equal to r into omega. Alright, already you studied in uniform circular motion chapter. Alright, again if you take the derivative once again, so dv dt you can write it as r d omega dt. So dv dt is what? Linear acceleration. dv dt is what? Linear acceleration. So I am writing it here because v, everybody knows, this is linear acceleration, and d omega dt, change in angular velocity with time, we denote it by alpha, and alpha is the angular acceleration. Alright, v is the linear velocity and omega is the angular velocity. Is that clear? So these are the important relations you are supposed to remember for rotational motion chapter. When a rigid body rotates, in that case linear velocity is equal to the radius vector into the angular velocity, magnitude I have written, and then linear acceleration is given by radius vector into the angular acceleration, and angular acceleration is what? Rate of change of angular velocity, and rate of change of angular velocity means what? D omega dt. Alright, so these are the two relations. The relations I am writing within the rectangles you are supposed to learn and remember for answering the conceptual questions as well as the numericals. Next is coming equations of rotational motion. Alright, now what are the equations of the translational motion? I hope you can remember. The first equation is V is equal to U plus AT. Alright, second equation is S is equal to UT plus half AT square, and third equation is V square is equal to U square plus 2AS. Alright, now what will be the corresponding equations in rotational motion? Alright, now you know that in case of translational motion velocity, linear velocity, it should be replaced by angular velocity in case of rotational motion. In case of translational motion linear acceleration, it should be replaced by angular acceleration. Alright, so you see, if you replace it in case of rotational motion, then you see V will be replaced by omega. So omega is equal to omega naught plus alpha into t, where omega is the final angular velocity. I am writing it here. Omega is what? Final angular velocity, and omega naught is what? Omega naught is initial angular velocity. And what does alpha represent? Already you know, alpha is the angular acceleration, okay, and t is the time taken. Now come to the second equation of motion. In case of translational motion, you can write it as S is equal to ut plus half at square. In this case, it should be replaced by theta. Linear displacement should be replaced by the angular displacement. So what does theta represent? Theta is the angular displacement. How we measure the angular displacement? When a body rotates, then at certain instant of time, the angle subtended by the body at the center is the angular displacement. Alright, so here S should be replaced by theta. So theta you can write it as omega 0 t plus half alpha t square. So you see, if one remember what are the equations of motion in case of translational motion, easily one can write what are the equations for rotational motion. So what should be the third equation of motion? V should be replaced by omega square, E will become omega naught square, then A will be alpha and S will be theta. Is that clear? So these three are the equations of rotational motions. Now derivations of this you don't have to do, because in your from your portion the mathematical analysis chapter is removed, so I have not taught you the differentiation and the integration, so you will not understand the derivation in terms of differentiation and integration. That's why I am just telling you that how to write, just by comparison method, how you can write down the equations of the rotational motion from equation of translational motion. That means these three equations of rotational motion you must learn and remember. Now the concept I am giving you, that is very important for this chapter. Rather, this is the, what I can say, backbone of this chapter, that concept of moment of inertia. Alright, what is moment of inertia? Inertia you studied. All clear? Inertia you have studied in the lower classes, and you know inertia is the property by virtue of which a body opposes any change in its state of rest or state of motion. Now it is concept of moment of inertia. What is moment of inertia? The property by virtue of a body, the property of a body, by virtue of it, it opposes any change in the state of rotation about an axis is called moment of inertia. Alright, and moment of inertia of a particle is measured by the product of mass and square of its distance from the axis of rotation is the measure of the moment of inertia. Means just you consider, suppose this is the axis of rotation and here is the particle, it is rotating. Then you see the particle is suppose at a distance r from the axis of rotation. This is the axis of rotation. Then moment of inertia of the particle. Remember what I said? Moment of inertia of the particle is given by I is equal to product of mass and square of its distance from the axis of rotation. So what is the distance of the particle from the axis of rotation? R. So square of the distance from the axis of rotation. So moment of inertia of a particle is given by mr square. Alright. Now suppose instead of a particle you have taken a rigid body. Suppose this is the rigid body and it is rotating about this axis of rotation. In that case I will be sigma mr square. Sigma I is equal to 1 to n mri square. What does it mean? If you consider that the rigid body, it has n number of particles. Alright. So for each particle, what will be the moment of inertia? Mr square. So what is the entire moment of inertia of the rigid body? It will be sum of the moment of inertia of the individual particles. Why the sum of? Because moment of inertia is a scalar quantity. Alright. Moment of inertia is a scalar quantity. So, if you want to add the moment of inertia of all the particles constituting the rigid body, then simply you have to add it. So, it will be the scalar sum, so not a vector sum. So, you can write it as sigma I is equal to 1 to n mri square. This is moment of inertia of a rigid body. Alright, this is the measure of moment of inertia of a particle. I is mr square. This is the measure of moment of inertia of a one particle. But if it is a rigid body, in that case we write it as sigma mri square. You know already that sigma represent the summation. Alright. So moment of inertia of a rigid body is given by sigma mri square. Here girls, sorry, because here you cannot consider that all the particles may have the same mass. So you can write sigma miri square. I will also vary for mass also, because mass of all the particles constituting the rigid body may not be same. So I will be sigma miri square. Now, according to our concept that if a rigid body rotates about an axis of rotation, if you consider this is the ith particle which is at a distance of ri from the axis of rotation, then you can write it as sigma I is equal to 1 to n miri square. Alright. Now, the next concept is radius of gyration. So you see, in this case, instead of considering the rigid body as a collection of particles, we may apply just like the concept of the center of mass. We know what? That center of mass is the point where the entire mass of the body is concentrated, isn't it? So you see, in that case, what will happen? If I apply the concept of center of mass, then you see, if this is the center of mass of the rigid body, then instead of the rigid body, I may consider a particle which is having a mass big M, where big M is the sigma mi. Big M is what? The mass of all the particles. Is that clear? Then you see, if I consider it as one particle, then the distance of the center of mass from the axis of rotation, it is denoted by K, and that is the radius of gyration. And K is chosen in such a manner that I will be, moment of inertia will be given by m into k square. This k is known as the radius of gyration. Alright, so how you can define what is the radius of gyration? The distance of the particle or distance of the point where we consider that entire mass of the body is situated, and it is the value of k or the radius of gyration is such that I is given by m into k square. Alright. So this k, you see, according to this relation, is given by I by m. So if you cannot write what is radius of gyration in sentence, then you can just show it in the diagram like this. Here we are assuming instead of the rigid body, that entire mass of the rigid body is situated at the point M, and the distance of the point from the axis of rotation is such that moment of inertia is given by M into K square. In that case, K is known as the radius of gyration, and radius of gyration is equal to under root moment of inertia divided by total mass of the rigid body. So this radius of gyration is an important concept for 1 mark question. So you must learn and remember. Now let us consider that a body is rotating about an axis passing through the fixed point O. Now here if the derivation comes, then whatever I am saying verbally, you are supposed to write in the answer script. Okay, I am not writing everything because the board I am using, it's too small. So whatever I am saying, again I repeat that whatever I am saying verbally, you have to write in the derivation in exam if it comes. Okay. So suppose there is a body which is rotating under the action of a torque tau about an axis passing through the fixed point O. Alright, and let us consider the angular velocity with which the body is rotating is omega. Is that clear? Now, if you consider instead of an entire body, and we are considering that the entire body consists of several particles, n number of particles. Alright, now if I consider only one particle which is at a distance r1 as I have shown it from the axis of rotation, then you see acceleration of the particle, I am writing it and naming it as term 1, acceleration of the particle, linear acceleration, it is given by r1 into alpha. Is that clear? Remember that angular acceleration and angular velocity for all the particles, it will be the same. Not that different particles will move with different acceleration, angular acceleration. Then what will happen? The body, it will just get deformed, isn't it? Because different particles cannot move with different angular acceleration. So you see A1 is equal to R1 into alpha. So, if you consider that what is the force acting on the particle? Force acting on the particle F1, I am denoting it by F1 because this is the first particle. It is given by M1 into A1. So, you can write it as M1 R1 into alpha. Alright, so you see this is the way you can write what is the force acting on the other particle. It will be M2 R2 into alpha, isn't it? And what will be the force on the third particle? It will be M3 R3 alpha and so on. Now this is the force. So what is the moment of force? Moment of force F1 acting on particle R1, you can write it as tau 1 also. Moment of force F1, it will be given by R1 into F1, isn't it? So you can write it as F1 is M1 R1 alpha. So it is becoming M R1 square alpha. Is that clear? So you see, moment of force F1 is m r1 square alpha for the first particle. Then what will be the moment of force for the second particle? m2 r2 square alpha, like that. So what will be the total moment of force acting on all the particles? Total moment of force or torque acting on the body. What you can write? What it will be? Torque acting on the body. You can write it as m1 r1 square alpha plus m2 r2 square alpha plus m3 r3 square alpha, so on. Let us consider last particle be nth particle. So mn rn square alpha. Okay. So one can write what will be the torque. You just add all the torque acting on all the particles, because you see here you may ask that torque is a vector quantity, then how I can add them? Because as we are considering the particles belongs to the same rigid body, so all the particles, they are moving in the same direction. So torque acting on all the particle, their direction is same but the magnitude is different. Okay, so that's why while finding the total moment of force, you can just add the moment of force acting on all the individual particles. So you see, you can write torque is equal to, you can take alpha common from all. So it will be m1 r1 square m2 r2 square plus mn r1 square. So one can write it, it will be alpha into sigma mi ri square, I is equal to 1 to n. Now what does it represent? It is nothing but moment of inertia. Is that clear? So you see, what is the relation you have got? Torque is equal to moment of inertia into angular acceleration. Is that clear? You have to remember this. If that moment of inertia, torque is given by moment of inertia into angular acceleration. Torque is equal to I into alpha. Another important relation of this chapter for solving the numericals as well as for solving the conceptual questions. So you must learn and remember it. And this derivation also you must practice, because in this derivation no calculus is there. Calculus method is not used. So it may come in the exam. So you must learn the derivation also. Thank you, girls.